All right, welcome back, everyone. So these are the final AP Physics 1 2022 FRQs. Today I'm going to be doing the longer of the 5 questions. So questions 2 and question 3, the qualitative quantitative translation, and the experimental design questions. All right, so we've got 2 moons orbiting a planet, and the mass of each moon is significant, but less than the mass of the planet. And at some point their orbits are aligned. So the first thing that we have to do is draw free body diagrams for both of the moons. And it does say that each force should be represented by a distinct arrow on the dot and pointing away from the dot, which is pretty standard, of course. So on moon B, we should expect to see 2 gravitational forces, one from the planet. So I'm going to call this FG, comma, P for planet. And then I am also going to have a gravitational force from moon A as well. Now, do note that I have actually gone ahead and drawn the gravitational force for the planet larger, and that's because of the orbits there. We would expect to see something like a larger force for the planet because it weighs more. And then we would also expect to see something like a smaller force from the moon because it weighs less than. So these would be our free body diagrams. All right, and notice how FGB is equal to FGA. I tried to make them equal. I guess maybe it doesn't necessarily look like that, but I did the best I could with this. All right, so consider the net gravitational force exerted on each moon. Justify why the net force exerted on moon A could be larger than the magnitude of the net force exerted on moon B. Well, the reason why I would say that the net force could have a larger magnitude on moon A is because for moon A, well, if you take a look at my free body diagram, the 2 forces acting on it add together due to gravity being an attractive force, due to gravitational forces being attractive, meaning that moon A and moon B experience forces towards each other. However, for moon B, the forces subtract, as shown in my free body diagram. Now, that alone is not actually enough to say that moon A would have a larger net force. The thing I would also have to say is that if RA and RB are comparable to each other, then I would say the net force would be greater on A in light of this. All right. Okay, so I'm missing an N right there. Okay. And so essentially what this is saying is that if RA and RB are comparable, then the forces from the planets are comparable. So, maybe I should write that down as well, but I kind of ran out of space here. So if RA, RB are comparable, the 2 gravitational forces from the planet are comparable, are nearly the same. And so therefore, the net force would be greater in light of those facts. And so that would be a good description as to why moon A could have the larger net force. All right, so moving on then, question B, part 2, justify why the net force exerted, and I can't actually see that due to the different panels that I have on my screen right now, but I'm assuming that's talking about why the net force exerted on moon B could be larger than the net force exerted on moon A, which is easy enough for me to answer then. Because if RA is much larger than RB, so that's what the 2 greater than symbols represent. So if RA is much greater than RB, then the gravitational force FGA is very small, and the force from the planet on A is very small. Therefore, the net force on moon B would be approximately equal to the gravitational force from the planet on B then. Whereas F net A would be approximately equal to 0 then. And so obviously that means that moon B would have the larger magnitude of the net force then. All right, derive expressions for both of the following quantities, the net force exerted on moon A and the net force exerted on moon B. Well, that's actually easy enough because for moon A, all I have to say is that the net force on moon A is equal to Fg, comma, planet on A plus Fg from moon B. Well, we do know that gravitational force is capital G, so I'm going to get G. Actually, I do apologize. I'm also going to put the mass of the moon outside as well. And so then the planet has mass m sub p, and it's a distance r a from the moon. And then in addition to that, what I'm going to have is mo for the mass of moon B divided by, now what's the distance between moons A and B? Well, it's going to be RA minus RB squared. There we go. And that gives me an expression for my net force then. All right, so thinking about net force on moon B, what's that going to be equal to? Well, it's going to be equal to gravitational force from the planet minus the force of gravity from moon A. The reason why it's minus is because the two are pointing in opposite directions, and I'm doing forces into the circle being positive, forces out of the circle being negative. So I'll start with the same thing, except now for the planet on moon B, I'm going to have R sub B. So that's looking good. And then I'm going to have minus m naught RA minus RB all squared. So that'll give me my distance squared then. All right, could the expressions in part C support my reasoning from B part 1? So that was saying that if RA is comparable to RB, then in that case, I would expect to see a larger net force for moon A then. All right, so could that support this? Well, if RA is comparable to RB, and so I'm actually going to say yes. And I know that I know that I'm missing quite a bit of space here. It has to do a little bit with my recording software. So, okay, there we go. That's a little bit better. All right, so yes, it could. And the reason why is if RA is comparable to RB, I just realized I made all of these lowercase. I apologize about that. There we go. So if RA is comparable to RB, then then I would say that both of the net forces are comparable. Sorry, not both of the net forces. I apologize. That's not what I meant to say. Then the forces from the planet on A and B are comparable. And the second term in each expression is the same. Now that should be pretty clear from my expression, right? The second term is always going to be the same. The difference is just one is positive, one is negative. The reason why they're the same, obviously, is Newton's third law. And so the second term in each expression is the same. The forces from the planet on A and B are comparable. Therefore, I get a larger number, larger magnitude for FA due to the positive sign, due to the forces adding together. All right, could my expression support my reasoning in part B, part 2? Well, part B, part two, I said that if RA is much greater than RB, then the gravitational force FGA is very small. FG planet A, I believe. Yeah, and also, sorry, both of the forces on Moon A. I'm starting to get my words mixed up. I apologize. Both of the forces from on Moon A are going to be very small. So the answer to this is yes. Yeah. So if RA much greater than RB, then and I did just realize, I don't know why I didn't catch this sooner, but there should be two squares for the two first terms in my net forces expressions. I don't know why I didn't catch that, but I went ahead and fixed it just now. All right, so if RA much greater than RB, then I get that FA is approximately equal to GMO RA squared, and then I have MP plus MO, and FB is approximately equal to GMO MP over RB squared. And now the thing to actually realize here is that if RA and the first term is far smaller, due to depending on 1 over RA squared. And so that should be sufficient then. So again, the thing to realize here is that if you have a much larger term in the denominator, you are going to end up getting a far smaller value in the end then, right? It's like if I were to take 1 over x squared and set the limit as x goes to infinity for people who have maybe taken calculus before. If you haven't taken calculus before, it's just a little bit of sort of estimation here, right? Well, if RA is quite a bit bigger than RB, then I would expect that the term that depends on RA inversely is going to be far smaller then. And so in addition, I'll have to also comment on that mass because the first expression has a mass in it. In addition, the extra, quote unquote, extra MO is not enough to compensate for this, since MO is not comparable to MP. And how do I know that? Well, if I go back and I take a look at the problem, it does say that MO is significant, but it is less than M sub P as well too. I know that you can't really see that because my drawings are still there, but you can always rewind and take a look at that too. All right, so let's go ahead and move on to the next page then. And wow, that's actually it for question 2. Right now I'm looking at my clock and that's only 14 minutes. So we actually did that pretty quick then. All right, well, I guess let's just go ahead and move on to question 3 then. So I'm feeling pretty confident with question 2. All right, wheel is mounted on a horizontal axle. There's a light string and wrapped around the wheel's rim several times, and there's a block in free fall. Two students are discussing how different forms of energy change. One student says that kinetic energy increases as the block falls. The other says this is because gravitational potential is converted to kinetic. So they want to figure out, is energy conserved, in other words, if you have a closed system. All right, okay. So design an experimental procedure that the students could use to compare the increase in translational to the decrease in gravitational potential. Yeah, okay, so we have to describe our procedure and everything, steps necessary to reduce experimental uncertainty. Okay, this is easy enough then, I think, because if I take a look at this, we're trying to figure out things about gravitational potential energy, which is equal to just mgh. And we're trying to figure out things for kinetic energy, which is given by 1/2 mv squared. So obviously one of the things that we're going to need to measure is the mass. So I'm just going to use lowercase m for that. And obviously I just need a scale for that. Now, in addition, G is a physical constant. I don't need to measure that. But if I wanted to compare gravitational potential and kinetic energy, I have to measure the height of the object. And so how would I measure the height? Well, I have a floor, I have a hanging block. And so what I could actually use for that would be one of two things. I could use a motion sensor, or I could actually use a meter stick. I think I'm actually going to go ahead and just use a meter stick. Now, if I were to use a motion sensor, that would, I believe, actually suffice as well, because in that case, what I would be able to do is I would be able to measure the velocity of the block as well too. But a meter stick is, depending on how high up that block starts, a meter stick could be more helpful. All right, and then if I wanted to measure velocity, I wouldn't just need a meter stick. I would also need to measure time to fall. So that would be delta t, and I would measure that using a stopwatch. All right, so my procedure, and I'm going to go ahead and just switch over to a text box for this. That's going to be a little bit easier. Okay, so my procedure is going to be the following. What I'm going to do is first, I am going to weigh the block using a scale to obtain its mass. The next thing I'm going to do is I am going to go ahead and measure the block's initial height using my meter stick. The third thing I'm going to do is I am going to release the block from rest and record the time taken to reach the ground using stopwatch. The fourth thing I'm going to do, and of course I'm running out of space here. The fourth thing I'm going to do is I'm going to calculate the block's final velocity using a kinematics equation, actually. Now, in terms of that, oops, what happened there? I do apologize. All right, there we go. I apologize about that. I have no idea what happened to that text box, but it's working now. All right. Anyway, I'm going to calculate the block's final velocity using a kinematics equation. So what's that going to look like? That's going to look like delta y is equal to 1/2 initial velocity plus final velocity times time. But because initial velocity is 0, that's just going to be 1/2 vf delta t then. And so then after I have calculated the block's final velocity, then step number 5 is going to be repeat steps 1 through 4 at least 3 times and average the measured and calculated values. Now, why am I doing that? To reduce experimental uncertainty. You always need to have something like this in your response. And the best way to reduce experimental uncertainty is going to be multiple trials. All right, explain how the students could determine the kinetic energy immediately after the block reaches the floor using the quantities indicated. Well, what I can do is, again, I can find final velocity using 2 delta y over delta t, as indicated in part A. And then I can calculate kinetic energy using 1/2 mass times final velocity squared, which is going to be 1/2 mass. Final velocity will be 2h. H, of course, would be delta y. So maybe I should go ahead and change all of those over delta t. And so that's going to reduce down to 2mh squared over delta t squared. There we go. That's in terms of all 3 of my measured quantities then. All right, moving on over to the next page. The graph represents the change in gravitational potential energy and the translational kinetic energy. On the graph, draw a line or curve to represent the rotational kinetic energy. Well, I should expect for energy to be conserved, so we're going to start with 0 And then it looks like the kinetic energy translational goes up to about 0.15. So I would expect about 0.25 joules of rotational kinetic energy. And so I should expect to see a straight line that looks something like this. And that would give me the rotational kinetic energy because of conservation of total energy then in the block wheel Earth system. All right. Finally, part D, kinetic energy as a function of omega squared, rotational velocity squared. And we are asked to draw a best fit line. So let's just go ahead and get our handy best fit line drawing thing right here. Wow, these data are very spread out, but that's looking somewhat decent. All right, using the line, calculate an experimental value for rotational inertia. Well, I do know that k sub r is equal to 1/2 I omega squared. So what I'm going to get is that kr over omega squared, which is the slope, should be inertia over 2. Therefore, inertia is 2 times the slope. Well, what is the slope in this case? I have to find 2 points on my best fit line. And it looks like, let me go ahead and change the color just so you can see this better. It looks like this point right here. And this point right here seem like they're going to do that. Okay, so that is at 15 for omega squared. And let's see, 1, 2, 3, 4, 5. So that's going to be at 0.52. 0.52 joules. And then if I take my second point, 6, 7, 8. So this is at 8. And this is at approximately 0.32. So my slope is going to be 0.52 minus 0.32 divided by 15 over 8, which is 0.2 over 7. And I'm going to go ahead and use my calculator for this just so I don't make another silly mistake like I did on the physics C questions in the E&M section. And so that slope is equal to 0.029 approximately. Therefore, what I can say is that the inertia being 2 times the slope is going to be equal to about 0.06 kilograms times meters squared. Or in other words, I could use another unit, and that's going to be joules times seconds squared. And I'm actually going to go ahead and circle those units because those units are actually closer to what we have on our graph then. Kilograms times meters squared is typically the units you'll use for inertia. And if I were to actually write that out, right, a joule is kilograms times meters squared per second squared. So that should equal units of inertia times 1 over second squared. Remember that radians don't actually get included when you're using SI units like this. And so therefore, what I'm going to find is that the units of inertia are kilograms times meters squared. Or again, as the graph shows, joules times seconds squared. Either would be acceptable for this problem. All right. And so that does it for question number 3. That does it for the AP Physics 1 2022 publicly released free response questions. So I hope that you found these helpful. Hopefully it gives you a little bit more confidence with your work as well. Or if not, hopefully you're feeling a little bit better as to how to go through and solve and think about these questions as well too. But thank you so much for watching. I hope that you learned something, and I'll see you all on the next video. Take care, everyone.